We can start the question time, and I have one question, a recursive question, let's say, about N2O emission. You just talked about reduction of NO by mild combustion, but you didn't show us N2O emission of those conditions. In low temperature ammonia oxidation, N2O emission should be very large. Please comment on N2O emission data of your findings. And there is also a second one question that is on the same channel. So Pino,
yes.
You can comment on that.
Yes, thank you for the question. Of course, N2O emission are a big issue. Unfortunately, we cannot measure N2O emissions, but it's possible also to, N2O emission may be released for ultra lean conditions. And for the use of a burner under non-premixed mode, it may avoid the formation of N2O species. We performed some safety simulations using, relative to our burner. It was possible to see that N2O were formed in the lean part of the burner during the mixing process, but then they were strongly reduced, step into the rich conditions. So we cannot measure N2O, but at the same time, applying the non-premixed strategy and controlling, of course, the equivalent ratio of the system, we can think that N2O emission are not present from our burner.
Okay, thank you. So there is another question from Nakamura. Thank you for nice presentation. Regarding O2 effect on NO in ammonia mild combustion, have you observed it in experiments? The paper on progress in hydrogen combustion science by Glarborg pointed out that models predict the H2O effect on NO, while reactor experiment showed no H2O effect on NO.
Okay, thank you for the question. Maybe it depends on the amount of water that is present in the systems. Anyway, there are many other evidences from literature, and water is used as a conventional system to abate NOx because it can enlarge the NOx window where the NOx window. For instance, there are also some contribution from the University of Cardiff, where they have a premixed turbulent flame. They add water, and the water consumes O radicals, and of course they can limit also the thermal NOx. So I'm a little bit surprised about this declaration that water does not have any kind of effect. Also because there are many papers from Glarborg himself that they show that water can limit the production of NO.
Okay, thank you. The other one is how to handle high temperature corrosion when preheating ammonia, since it may be necessary for mild conditions. But
regarding our experiment, we don't need to, we can preheat or not preheat ammonia, but in a way, the important thing is to use material that cannot be corroded by ammonia. For instance, stainless steel is a solution, Of course, it is necessary to avoid materials like copper that can be, can be drastically damaged by ammonia. But if you use simple stainless steel, you can handle ammonia without any problem.
The other one is from Bassam. Thank you, Pino, for the talk. What do you expect do we expect the effect of pressure under mild condition to be? Has there been any computational studies of effect of pressure on the kinetics under these temperature and mixture conditions?
To my best knowledge, I don't know many work about that. I know that there are some contribution from Adelaide, but I'm not. I remember their paper relative to the mild combustion, to the effect of pressure on mild combustion, also for ammonia. Of course, increasing the pressure, the region where mild combustion can be attained slightly reduces. But of course, it is still possible to work under mild operative condition. Of course, it depends on the pressure, but having looked at the NOx chemistry, many other contribution, for instance, from the group of Professor Kobayashi or from Valera Medina, they say that higher pressure are more beneficial for NOx reduction because of many reactions are important, like H plus OH plus M is important, which produces water. Thus, it means that the concentration of H and OH radicals is slightly decreases, so the NO formation is slightly decreased as well. There is also a contribution by Professor Glarbor about the NOx. And they say that increasing the pressure, the NOx chemistry shifted to higher temperatures. So maybe under mild condition in pressure, still it would be possible to couple mild combustion with the NOx chemistries.
Okay, thank you. I have a question for Mani, and it concerns to pyrolysis kinetics. It seems that it is relevant not only in pyrolysis, of course, condition, but also for ignition of ammonia and so on. It seems that there are high uncertainties on kinetics of pyrolysis, and in general they ask for more experimental data, and also maybe not still clear what are the all the NXHY species that can be involved in this part of kinetics. Can you comment about that, and also on how the theoretical studies can help in identify the potential species that we can still add in pyrolysis set of reaction?
Okay. So I think, yeah, for ammonia pyrolysis, there was some work done at very high temperature, but probably we need, as I mentioned in the beginning, now with the cracking of hydrogen just by thermolytic means, non-catalytic, as we showed in that post-combustion heat exchanger design. Actually, it would be interesting. What's missing is ammonia hydrogen pyrolysis. So indeed, we have some data for ammonia pyrolysis, but in the presence of hydrogen, as a hydrogen is being formed during the cracking process, it's going to continue as a pyrolytic reaction. And I think the initial amount of hydrogen will have an effect on the pyrolysis process. I agree. I think things like the hydrazine and diazine, the intermediates pyrolysis, there's limited data there. Yeah. So hydrazine as a feed or as a fuel is difficult to work with, very dangerous, toxic, difficult to manage. I think the last papers that looked at hydrazine are already 30 years ago, where maybe the safety requirements were less. So I think today we must rely heavily for some things like hydrazine kinetics, probably much more on theory than on experiments. But hydrazine is a fuel that's used in aerospace applications and as a propellant. So there's been some works on hydrazine molecular dynamics studies, most of them at low pressure, I think, related to satellite propulsion and thrusters. So yeah, I think there's still scope for looking at theory based on some of these reactions. And I think most of the focus may be on actually the lower temperatures. So say, let's say 500 to 800 degrees, 500 to 900 degrees Kelvin, where you're going to use ammonia in cracking applications, rather than the high temperature, traditional high temperature pyrolysis in a combustion system.
Okay, but I understand that this reaction, pyrolysis set, is very sensitive also also affect this set of reaction also intermediate and low temperature kinetics, and so maybe also in your opinion, which kind of experimental test could be done in this low intermediate temperature range, in which kind of system, what we miss?
And I think also as we add in hydrogen, those intermediates for in the traditional ammonia pyrolysis become more important. So things like when you add hydrogen to ammonia combustion at lower temperatures, you're going to get the N2H4 formation, N2H2. So that even in, say, hydrogen ammonia oxidation system, I would say the pyrolysis intermediates become more important at lower temperature. Pino showed some data from rapid compression machines from Pocket et al. I think that was good data down to about 1000 Kelvin, but below that, we don't have much ignition delay time data for ammonia hydrogen mixture. And of course, as speciation data, I believe some of the first was the one we did at KAUST in jet stirred reactor, but we know JSR has limitations in terms of residence times. So probably some flow reactor data with the MBMS or synchrotron-based techniques for studying the intermediate species would be important. They'll probably be able to measure hydrazine at low temperatures using, say, synchrotron-based photonization mass spectrometry coupled to a flow reactor or to a flame. And I've not seen data for that yet. It could be useful.
Oh, thank you. Another question.
Maybe we will see it at the symposium. I don't know. I have not received the papers for
Let's
review
hope.
yet.
Let's hope. But I think that we need a huge amount of data. So welcome the possible paper at the symposium. But I think that we need more and more data on this issue. And the other point, Gaetano, you are.
So I mean, kind of following up on your question, Mara, it's and connecting to what Barlow was presenting at the beginning of the day. So we are able now to do some canonical turbulent canonical flames, and we're going to collect some data compared to the CFD model, so we can get things like NO. We're working on other minor species to make it quantitative, as Rob suggested. But my question is, are the kinetic models accurate enough that we can hope that the CFD can match the results, or is it almost a useless exercise because the kinetics is wrong, so you put something wrong in and we cannot expect to get the right results at the end? Maybe both Mani and Pino can comment on the state of the art in a sense here. Are we doing something useless?
Go ahead, Pino. I cannot tell my colleague what he's doing is useless.
Of course, I think that especially for this range of temperatures, there is a huge uncertainty on the kinetic mechanism, and even more updated mechanism may present some discrepancy with experimental results. But for the most, the common comment that all these modelers they do is relative to the also to the role of H2NO species and to the M2HX species. Maybe for those kind of reactions, the uncertainty is very huge. There are many third body reactions. The pressure dependence of this reaction are not very well known. So I mean, to develop a robust scheme, maybe there is something else to do. Of course, for instance, we try to model some results from the burning using several kinetic mechanisms, also in the CFD simulations. Of course, mechanisms are very dependent on the kinetic mechanism we choose. So there is a lot to do, I guess, before having a kinetic mechanism that is reliable, robust, and to be used in CFD. Also because under CFD, if we operate under non-premixed mode, of course, the chemistry is important from ultra-lean to rich conditions. And for the most, if you model the laminar flames or ignition delay time in under rich conditions, the models are not very robust. So maybe what to answer also to the previous question that Mara made to Mani, maybe we need to focus the attention a lot on the rich conditions, because over there the discrepancies between models and are huge, and there are few data.
So I mean it was useless what I'm doing, but what I'm suggesting is maybe before going to turbulent flame, is there a role maybe some laminar flame configuration can play in helping with the chemistry and validation of the chemistry? Can things like counterflow flame or laminar flame burner play a role in this as a step in between what you guys have been doing great until now and the turbulent flame? Does it play a role of there is no advantage in that?
You know, typically we would like to counterflow strained ignition and extinction measurements are always useful. And I think previously we heard from Dr. Barlow about the differential diffusion effect. So definitely once you come to diffusive strained condition that of say ammonia hydrogen mixtures, I think that would be relevant. We have started looking at like that ammonia hydrogen diffusive strained extinction, but also other adding in hydrocarbons, yeah, like methane, propane, ethane with ammonia. Counterflow speciation, I have not seen anything out there yet for ammonia hydrogen mixtures. That could be, again, that could also be useful before going to say a turbulent jet flame. I think from premix flame, there's already a fair bit out there. Yeah.
No, we cannot hear you.
Yeah, that's Bassam Dali. I just want to comment about the turbulent flames. I guess from my experience, we should never hold back on collecting data, even if the chemistry is not really ready for it. So I think my experience is that we collect as much data as we can, and eventually sort of the models will identify where we're failing, so we go back to the laminar to be able to then to resolve it, so we could actually further improve it. One of the data we just collected, haven't published yet, relates to strain and extinction, and what we noticed is very interesting phenomena, especially when you have hydrogen. You start getting these islands of burning pockets that not necessarily sort of you see in hydrocarbon flames. So the extinction reignition or the turbulence chemistry interaction is likely to be a challenge in my view, and we're going to try and contribute in that regard, and including hopefully in the future under pressure as well. So and mild. So, but definitely we need every front to be tackled at the same time. But I think we learned quite a bit from measuring turbulent flames to what we really need in the laminar side.
Okay, I think in general, I think that my opinion is that we need data also from elementary reactors, steel, from jet steel reactor, plug for reactor, and so on. Of course, we have other problems there that we have to face with, for example, the other experimental artifact, but there are ways to avoid them. The whole problem with surface effect. Maybe Pino can comment a bit on this after. And the other point that I would ask to the kinetic community is on third body efficiency. Why it is generally disregarded is, you know, the attention is very low on this point in general in this on evaluation, accurate evaluation of third body efficiency. That maybe it is also dependent on the condition, on I don't know, but maybe it is a lack of information and attention on this point. I ask a comment from Pino and Mani on that.
I think there's been quite a bit of work on third body efficiency in traditional combustion systems, for example, from Aaron Jasper, now at Argonne National Lab. But again, maybe for a handful of species, not so extensive, because typically you're doing very expensive molecular dynamics calculations to get these things nailed down. Of course, Michael Burke has done some work on the effects of pressure dependence, third body efficiency, but specifically to ammonia systems, yes, we have not seen that yet. So I think it's going to be different, right? When you have a lot more NO around, what is third body efficiency of NO? Say hydrazine, if this is made in large concentrations. Yeah, you're right, Mara. One step at a time, though. You know, going to those types of elaborate calculations is very expensive.
Yes, Mani, but I understand this. But this is if even maybe in ammonia highlights even more this problem. This is also an issue in for kinetics of traditional fuels. So it is not, you know, is maybe an old issue that we have to take in mind when we optimize the models, or also standard fuels of methane and so on. I know the works from Jasper and so on, but you know, now I see that the attention also for of modelists of kinetics, when they update models, is to focus the attention mainly on Arrhenius parameter, and generally they disregard the relevance of third body efficiency. But
so actually, there's a research professor here, Thibaut Ghiberti. He's starting to look at chemiluminescence in ammonia-related systems. And for that, of course, we have to look at collision efficiencies for different collider molecules. And some of the computational scientists here, theoreticians, are starting to look at that. But again, it's very challenging calculations. But again, the hope is studies done on the fluorescence, chemiluminescence side. Chemiluminescence will be translatable to some things we want to do in the combustion as well.
Pino, you can add something on that?
Yeah,
okay. Oh, Mani is still.
No, I was gonna comment something else. If he wants to respond to this, it's fine. Go ahead, Pino.
Okay, okay, it's you wouldn't mind. Okay, just a brief comment on third body. I guess that third body species have been for a long time. I mean, this topic is particularly relevant for mild combustion condition, but also for pressure. So, of course, there is a huge uncertainty on third body efficiency. Especially, for instance, for I mean, in the case of mild combustion, we noticed this point also just referring to water, because of course under mild operative condition there is a strong recirculation of exhausted gases, so the process occurs in presence of great amount of water, great amount of CO2, and conventionally they have a strong third body efficiency mechanism. By mechanism, for instance, water with respect to nitrogen is reported to be to have a efficiency like 12 times higher than nitrogen itself, and also CO2. But the problem is that going to work to pressure and going, of course, to work under mild operative condition where recombination reaction are important, when the reaction like H plus 2 plus M is important. Of course, this is a very hot topic, because of course we cannot think to model properly mild combustion processes without considering this aspect. In addition, there is also another aspect that third body efficiency may change with temperature. I mean, they are temperature dependent. Usually this point is completely disregarded, especially if when considering, of course, also the Arrhenius rate law, because they are defined just on the basis of a coefficients. But there are some papers that clearly show that third body efficiency may change also with temperature. Then in the case of ammonia, I mean, this should be, in my opinion, a very important topic, because essentially in kinetic mechanism, water has a very high third body efficiency because it's a polar molecule. So in the interaction with the HO2 radicals, there is a polar interaction. So this I mean, this interaction is described by means of third body efficiency, but also ammonia is a polar species. So probably also ammonia should have, like the N2HX species, should have a third body efficiency declared in the kinetic mechanism. So I guess that this is a very important topic if we want to model mild combustion system, but also system with respect to the pressure.
Yeah, I was going to add maybe if we're to move on to maybe some of the different things that could be studied with relation to ammonia and kinetics. So one is, besides traditional gas phase chemistry, I think we need much more work on surface chemistry interaction. We already talked about corrosion, But indeed, I think depending on the material of the combustor and the geometry of the combustor, there's going to be nitridation reactions on the surface. This can influence perhaps combustion over maybe longer durations of time. So we know corrosion is an issue, but what is the impact of the surface on, say, affecting ammonia decomposition or even species that are generated in the gas phase due to interactions with the surface? And we have started looking at surface reactions in tightly confined pre-chamber combustion engines, not for ammonia, but for hydrocarbons. Similarly, we should think in the case of ammonia, because surface interaction chemistry is more important, start looking at the effects of that. Another thing, ammonia, when transported as a fertilizer in large marine vessels, oftentimes is diluted with water and then separated afterwards for safety reasons. And let's say in the future, if we are to store ammonia in large concentrations for stationary power generation, do we need to separate out that water before burning, or can we burn an ammonia water mixture? This is something I don't see much research yet, but what about wet combustion of ammonia? And 5% water, typically done for safety reasons. Can we burn those mixtures? Again, crack the mixture, ammonia, hydrogen, water mixtures. What would be the kinetics of that? And then Pino talks about third body efficiency. It'll become even more important if we have to burn ammonia wet.
Maybe there are some results from Agustin on ammonia wet, and also in mild. You show Pino some.
Yeah, we perform.
So it is a good idea to use ammonia as it is with in solution, coupled with water and.
Were those from EGR scenarios, or from more for exhaust gas recirculation, or more for feeding actually water in with the ammonia?
Do you mean the data from Augustine or from mild?
Yes.
Yeah, is in I know the mild. This is water fed with ammonia. I suppose also in Augustine results. That is wet. What about your data, Augustine?
Yeah, we were able actually to inject water at different concentrations, and we went up to 70% of water ammonia ratio. It was really interesting to see those results, because when you get up to 40, you get a very good reduction of NOxes, and you keep the combustion stability. I can send that paper, and it's, I think, a really interesting area, just as you're saying, Manny, because it just opens a lot of opportunities to then use some of these wet ammonia blends, use some exhaust gas recirculation. That was the idea of doing some of these, and eventually just recover some of that water later down the line that you can then input into the combustion system. So it is a fascinating area. It just produces lots of pools of hydrogen oxide, oxygen, OH radicals, higher to the ones that you get with ammonia hydrogen. So it's a blends hydrogen ammonia at different concentrations with that water addition. I can send it over, but it's, I think, a really nice and interesting area to pursue further.
Also because water, as showed Pino, enlarge the NOx window, so enlarge or shift to a bit higher temperature. So it's good in general. So AGR or mild with ammonium water is a good approach. For a good solution, could be a good solution. I have just the last question about if there are any information on effect of ammonia when it is used when other fuel blends with hydrocarbon on soot from other pollutants like soot, nanoparticles, and so on. Do you have any data on that, any information, any idea, Manny?
Yeah, so we have a recent paper in combustion flame on that exact topic, ammonia addition to toluene flame, a co-flow, and also ammonia addition to an ethylene flame. We did find ammonia addition reduces soot volume fraction, but when we looked at the soot particle size distribution, it actually made some more smaller particles. But our main focus was on actually the, let's say, the chemical functionality of the soot that's being formed. And we did not find many nitrogen-related PAH species being formed in the co-flow experiments that we did. And we did not find that ammonia interrupts the traditional soot formation pathways by either incorporating itself into pyridine rings or aromatic rings and then impacting the soot formation. We just found that our conclusion was that ammonia blending just took away carbon by forming things like HCN, hydrogen cyanide. So the ammonia NH would react with the carbon in the ethylene flame and remove the carbon by forming HCN, and therefore you would get less carbon going to form benzene and aromatics. But others have postulated that NPAH, nitrogen-based polycyclic aromatic hydrocarbons, are important. We did not find it in our study, but it doesn't mean that this was just a first study. There was some work from Professor Roberts' group previously also looking at ammonia addition, but then looking at, I think, LII and scattering, just looking at soot volume fraction. Indeed, they found ammonia reduction. Ammonia reduces soot formation. Also, the group at Yale with Mitch Smook and others, Pfefferly, had looked at ammonia addition from a soot formation perspective, but the capability of reducing soot. But I still think there's more work to do on the detailed reaction mechanism and understanding that in detail. And probably what you want to do is some fundamental experiments of ammonia plus, say, benzene or PAHs, say in a stirred reactor or a flow reactor to see, or maybe ammonia plus pyrene to see does ammonia affect the pyrene dimerization rates in some way. I think there's a lot of things there that could be done to understand the mechanisms.
Okay, thank you very much for your answer. So I understand from this discussion that we have a lot of work to do, from a lot of data to collect and to fit all the needs that we have. Okay, I think that we can conclude our discussion. We have on time, Gaetano is true, is okay. So we have no other question from the audience. So thank you very much to both the speakers, Mani and Pino. Thank you for discussions. Thank you for following this section to all attendees. And I think that we have a break now. Okay, so we will come back in half an hour. I don't have the program now.
So it's in 20 minutes, right?
Okay, okay.
3:30. 3:30
Okay.
we start again.
Okay. Thank you. Bye.
I
See you later.